Okay, so hello everyone. Welcome to the Astronomy Department seminar. Thank you for being here on Friday morning. Today we have Ferdinand and Ernesto from the University of Dundee. Ferdinand is a second year PhD student at the University of Dundee, Scotland. Sorry, stop it. Not work. Since January 2024. He did his Masters of Physics with Astronomy at the University of Southampton. Ernesto is a first-year PhD student at the University of Dundee as well, where he's also completed his bachelor's and master's in physics and astrophysics. So thank you for being here. You too.
Okay, thank you for having us this morning. So we're gonna give you a presentation on the first year of North Face. So if you're curious what North Face stands for, it's Periodicity Hotspots, Accretion Stability and Early Evolution of Young Stars Clusters in the Northern Hemisphere. Yeah. So just a bit of flavor just to get you curious. This is the young clusters we are working in. So this is NGC 1333 by Ernesto, and this is Trumpler 37. That's by me. So this is the North Face team. So we have Aurora here as the lead, and there we are, Ernesto, Ferdinand. Yeah, it's a relatively large group of people who are working on young stars. Yeah. So just a bit of background. I think some of you might be familiar with this kind of picture. So it's essentially a summary on the life cycle of a star. So we kind of focus on just the beginning part of the whole process. So when we get young stars, they haven't yet reached the main sequence. Yeah. So we can see this in more detail by looking at the summary of star formation. So you get these large molecular clouds. Yeah, you have these kind of dense regions here that are very cold, very dense, a lot of particles in there. We get an external stimulation where it causes collapse. So this collapse forms a protostar. So really young star, it's embedded in that cloud, so it's not really visible. It has this flared disks. So, and we get this spinning due to kind of conservation of angular momentum. This process continues until essentially we get something similar to our solar system. So, North Face, we focus more on these stars here. So, this is what we see when we work with the data, look at the pictures of the clusters. So, we're talking masses of about 0.3 to about 4 M solar, ages of orders of mega years. So they're really young stars. So just this is a classical T-Tauri star. Just think of it as a type of a T-Tauri star. So as a classic. So we have certain processes and then structures. We have the sort of accretion disk here. So as the star is rotating, it rotates with the disk. We have these sort of accretion columns. So they are formed due to the interaction of magnetic fields from the star with the disk. So you get those funnels where materials kind of point to the star. You have these hotspots here. That's bit here. and the cold spots, those are the dark regions on the surface of the star. You also have these outflows. So the star throws up some of the materials being accreted. Yeah. And all of this kind of dynamical processes and structures, you can see them when you look at the data. You get this as some kind of type of variability. So why do variability? Why not phase? This is a photo. It's a picture from ALMA. So it's HL tau. It's a T tau star. We see quite a bit of details in there. We see the rings. We see the gaps, but we are more focused on the inner regions of what's happening in the star. So we can't really see much of the detail. So direct imaging doesn't work well. So just for size comparison, this is our solar system. It fits kind of on that inner region part there, but we want to go even more into the disk. So this is the image I showed before. You see it covers just a few sub-AU of the whole kind of structure. And this is what we want to observe, we want to study. So yeah, and again, direct imaging doesn't work well. So, and just a bit of scale, just to show you how dynamic these processes are. At distances of about the radius of the sun, we are talking about processes that would occur in a matter of days. And if you go to like half AU, so that's half the Earth's capillary orbit, so you're talking about processes that are occurring in orders of months. And if you go further, you're talking of years and decades. So yeah, and we are more on the starting bit, the days. Yeah. And as a solution, we are introducing the time dimension. Most of you might know some of these kind of facilities. So time dimension is kind of a new thing that's coming up. So more people are getting into it, trying to look at these structures and processes by using time. Yay. And this is the Javalambre Observatory. That's where kind of the north phase, the data from the north phase is coming from. Yeah, actually using the telescope similar to the one used by the S+ people. So you might be familiar to that. Yeah, that's kind of the same telescope. Yeah. And yeah, we have an image by Fisher here. So what it's showing us the magnitude versus the sort of the time scale of kind of the variability processes in young stars. So it moves from hours to centuries, so larger time scale. So, and we are kind of in the, let me see if I can get this right. So we've looked at the classical T-Tauri image. So we saw the things like magnetospheric accretions. We saw the star spots. We see they're occurring in sort of days to weeks. So it's in the shorter time scale. But you can also have these processes that occur in terms of decades. So that would probably need you to look for a very, very long time. Yes.
Thank you. Okay, so Ferdinand mentioned north phase, and that's our solution to this problem, right? So we look at 6 clusters, young clusters that are forming stars in the 2 square degree field of view, similar to S+. And in total, they contain over 4,000 young stars. So it's very good to do statistics over, for instance. And the young clusters in question are Trumpler 37, CFSOB3, IC5070, NGC 2264, IC348, and NGC 1333. Here in the picture in the background, you can see, sorry, let me see if I can get the pointer working. It might have gone off screen, yeah. There. It came back. Okay, so I work on these 2, which are in the Perseus region, and I'll be talking more about them later, and Ferdinand works on Trumpler 37. Then, how do we look at them? We look at them in 6 bands. So 4 broad bands, they're the Sloan Digital Sky Survey bands, the G, R, I, Z, and 2 narrow bands-ish. So we have the U band to look at ultraviolet light, and we have the H alpha band to catch specific accretion behavior. And we can see the bands here. Again, the quite large, quite large broad bands. We have the very thin one right at the H alpha peak. And then right here we have the U band, which is also linked to accretion, especially when you get that infalling material that hits the stellar surface. So Again, 6 photometry filters. It's a very international team, as you saw before, quite a few people. It's led by us in Dundee, but we have collaborators all over the globe. And it lasts 5 years, so that's how we can capture a lot of these behaviors that are going on. And again, here's a nice picture of the Javalambre telescope. Yeah, let's see, there you go. The 83 centimeter telescope is this dome over here. And yeah, it's a legacy survey, so you know it will be public and there'll be data products, which we'll talk about a little bit later. So, also, it's the source of the J+ survey, very similar to the S+ survey. So maybe some of you worked on that data. Next, so here is what we can see with north phase. That was the entire phase space of behaviors that were linked to variability in young objects, but we see that north phase covers the great majority of them. The only thing we're really missing out is a few Ori bursts, which last, you know, decades or centuries. But, you know, we cover long-term ones like X-loopy bursts, and there's just a lot of that behavior that's covered. And also thanks to the quite great sensitivity of north phase, we can even see things like narrow dips in the star spots that you might have seen on the cartoon before. So, how do we actually get this data? It's great to talk about what we can do with it. If we have it, how do we get it? First thing we do, telescope images. So here's an image of IC348, just what we get from the telescope. So pre-processed by them, you go flats by start. Oops, sorry. And this is just what would be a standard telescope image. Then we have to identify sources. So doing the photometry is different because the telescope was originally used for J+, which specifically focused on galaxies. So we had to redo the photometry specifically to look at stars here. Stars in cloudy regions, and of course, in star-forming regions, you have a lot of cloud. That's where the stars form. Therefore, you know, it's very important to actually catch these objects in the cloud because they're likely to be young or they could be behind. But we do need to examine them to look at their properties. And so we rewrote the pipeline from the Observatory Astrofísico de Javalambre. And now we're picking up a lot more of those objects in those very complicated regions. Then we make a deep catalog. So we combine the best images that we have, which would be good air mass, good full width half maximum. We combine them onto a deep image. And based on that, we can create our catalog for the objects that we're going to follow, because we do need a reference point since we're looking at variability, right? So this deep catalog, here's an example of one of those. We do have a little scale bar for scale, so that's about 1 parsec. This is quite close to about 300 parsecs, so that's why the 2-degree field, just about parsec. And picture of IC348. And we have to calibrate it, of course. So that's done with a few steps. The first thing we do is we select the non-variables as determined by Gaia. So it stars different magnitudes, so we have representative samples, but also that have a low standard deviation. So based on the repeated observations of Gaia, they're not deemed to be very variable, so good place to start if we want to calibrate. And what we do with that is then we get the Gaia XP spectra, and this is just an example one of a B-type in, it's called Omicron Persei in NGC 133. And essentially overlay the filters that we use specifically and generate synthetic photometry with the package Gaia XP. That way we can calibrate against these non-variables in the region and get very nice calibrations. And in fact, what we do see is that the calibration is strongly linear. It has a factor of about 2 from the readout of the CCD, so which goes about 13 to 16.5. But if we're looking at the calibrated magnitudes, 10 to about 18.5, 19. So very linear, which is good. No strange behaviors in the CCD. And that's it. And then finally, so now that we have the original calibrated, we can go through all the images that we take, cross-match them, and we get our light curves. So this is an example of a light curve from an object in NGC 1333. This gap right here is, let's see if I can find the, it's quite tricky, this thing. There it is, okay, it's come back. Okay, so this gap is an observing gap because the cluster wouldn't be visible then. But we see, just in this light curve, you already see some longer term variability, which happens on the scale of maybe about 50 days or maybe a little more. So this is just an example. We can see 5 of the bands. The U band is a little bit incomplete because it has to be taken on very, very dark nights. So we don't usually have light curves for all the objects in U band or very complete light curves. And so mostly we stick to this, and U-band will be more complete as time goes on in the survey. Because again, this is just the first year of data, and we're at plan for 5 years. So, okay.
Okay. How do we find our variable objects? So we're doing the interesting part. We can use variability indices, more specifically the Stetson and the SA04. So for now, we're getting 5 different Stetson indices per object and 5 SA04. That's because the U-band is a bit tricky to use right now. So we're gonna ignore that for now. So that's kind of an example of a histogram that you would get. So we get the Gaianan variables. So that's objects that we know are not variable. You plot them against the potentially young stellar object. So with that, you can get the variable tail. So what these indices do is to essentially measure variability from light curves. So the kind of core of the equation is to look at the deviations of the observed magnitude from a certain mean, then you would divide that with the uncertainty. So they kind of work in a similar way. So we got our variable objects. How are we sure that they are variable? You can look at the light curves. So you see the kind of fluctuations with time. So that shows some kind of form of variability. So here we see changes in color with time. That would be important in the next slide. We can even go further by looking at phase-folded light curves. We do that by using the Lomb-Skagel periodogram. So in simple terms, what that means is we take a bunch of frequencies, we throw them into the light curve. The one that fits the most will be taken as the kind of best frequency, and we can get the period from that. So we can get kind of periodic variables and non-periodic variables. So from here we see there's kind of a peak at about 8 days. So this object has a period of 8 days. So, and yeah. And
typical error in the photometry.
Sorry?
Typical error in the photometry.
Okay.
Compare the variability with the error.
The typical error in the photometry.
I'm not sure. I don't have the numbers at the top of my head.
It depends on the band, essentially. But but in the R band, which is very stable for us, you get errors on the order of 0.0, like 10 micromagnitudes, maybe something like that. That would be a good estimate. Yeah.
Okay.
It also depends on the cluster because they're calibrated differently because different distances. So, sorry.
Okay, that's fine. Okay. Now with our period, we can make a kind of a phase-folded light curve, so we can see even more interesting things. So something more interesting about this kind of phase-folded light curve. You see, initially we see that that's the kind of the red colors here. We see initially it's a bit messy. We don't really see that kind of periodicity in there. But when you go for longer distances, we see things become more and more clear. So that's kind of the uniqueness of our survey. So the fact that we are looking at kind of longer time scale, we are able to see kind of more detail. Problems. There's always problems. So something we kind of got across to was the existence of bad nights. So essentially nights that were kind of affected by the weather, sort of the air mass, the presence of the moon. So yeah. So we had to kind of take those out, and it's a quite important step because we see there's kind of an improvement in kind of the sensitivity of what we are getting. So we are removing that suppression that was caused by the bad nights. So in terms of numbers, the bad nights would amount to about 8 to 13% of the total number of nights. So not really high numbers than expected. So that's fine. Yeah. Now, examples of phase-folded light curves from Trumpler 37. So from this, you see that there are different kind of variability processes in there. The first one, that's caused by kind of the rotation of a star. So kind of a cold spot modulation. So as the stars are rotating, we get that spot in there. So there's kind of a decrease in kind of the magnitude that's being out there. So you get that kind of sinusoidal pattern. And the bottom one here, we have two spots. So they are kind of on in opposite sides. So the first spot, you'd get kind of that peak. And as it's about to disappear, we experience the second spot with the smaller peak there. And here we have a T Taurus star that's most likely a dipper. So there's some effect in the disk. So as for example, let's say it's a blob or something, as it passes through the line of sight, we get that decrease in magnitude. So as I said, all these sort of structures and processes are evident in our data as variability. And yeah, this survey, as you said, was meant for young stars, but you can still find stars that are not necessarily young. For example, we have these long period giant stars, so it has a period of 91 days. And we also have these fast rotating eclipsing binaries. So any of you interested in this? We have a lot of them, so contact us. Okay.
Okay, so again, we look at clusters, stellar clusters, because normally in the literature they're considered to be more or less at the same distance. They all share an age, right? Because they form from the same molecular cloud more or less at the same time. And also they share a formation history, they share a chemistry, because again, similar parent cloud, similar location, right? Well, it's not necessarily so simple. In recent studies, we see that clusters don't share a distance, like what's canonically known as the Taurus cluster is actually separated into various strands at slightly different distances. And in fact, the actual distance known as the Taurus distance is the least populated. It's actually bimodal, kind of right before and right after, it just averages out to that. So not so simple, which means different parts of the molecular cloud, and which means you also get formation happening at different times, right? So they don't necessarily have a shared age either. And therefore, their formation history is also going to be quite different. So essentially what we're saying is clusters have to be looked at with a little more attention than they might have been previously, especially with the new instruments coming out, for example, Gaia, that have been out for a while, but that need analysis. So we're going to start with the Perseus clusters. Here's a statue of Perseus with Medusa's head. Here's Perseus with its two clusters, you know, just the victims of and so we move to the first one, right? The bigger of the two, IC348, the distance of about 313 parsecs. It has quite a large age spread. I apologize for that. Has quite a large age spread, so very young populations, but some stars seem to be quite older, so 2 to 6 million years. And it has about 675 members. Again, this depends on criteria for membership, but that's around about what we find. Here we see the cluster center. So this is for a couple of reasons. First, we're trying to highlight that the north phase field has quite a lot of detail. You can see a lot of these stars in the central field, but also because this is originally like the region where this region is the region originally studied as the cluster, right? So IC348 would have been in this field, and then certain studies augment the field a little bit. But with this 2-degree field, we can actually see the entire region and see how far it extends if there are more structures to it. And again, just to show the survey, we have a Flying Ghost Nebula. So it has an edge-on disk that you can observe here, you know, just very red, so in the Z band, right? But you can see these sort of objects. Then we have NGC 1333, tiny bit closer, 296 parsecs, much younger, and about half as many members. So smaller, younger. We can see here a north phase a composite image, an RGB one, of the cluster, and you see all these dark patches, and you say, well, it's out of the galactic plane, maybe there's not so much stuff going on. Well, actually there is. There's a lot going on. These are just really thick clouds, which of course, it makes sense. It's young, it's forming stars, so this is where all the stars are going to be forming. And here you can see what would be the cluster center, right? By the way, all these astrophotography images are made by José Luis Lamadrid at the OAJ. So we just want to thank him for that. And yes, here we go. Here's the cluster center. You can see very embedded stars, even without the astrophotography, you can see it quite well. Okay, so remember we talked about cluster structure. What's going on here? Well, this is the Perseus region, and here we have the fields that we just looked at, and we see that this is IC348, and the blue members are what are generally associated with IC348 in parallax and proper motion. And here, the red ones are what are generally associated with NGC 130 and 33 in parallax and proper motions. But actually, after doing a study similar to the previously mentioned one, the Rocca Tagliata Taurus one, we find that there's actually a very, very large overlapping population that has its own specific proper motion and parallax. So essentially, it's an indication to a very complex star formation in the region that necessitates looking at wider fields, right? If there are these structures that are very, very large, you really do need to examine everything that's going on and not just zoom in on the cluster centers. So, whoops, wrong button. Here we go. So again, it's far, far, far beyond the classical limit of what used to be considered a cluster before the era of Gaia. So we can also find new members that are different to those using variability. And what we do is we use the indices, as mentioned before, because again, we're working with relatively large statistical samples. Again, it depends on the clusters, but Ferdinand has about 200,000 objects in his field of view, versus me, I'm looking at 20,000. So it's a little bit different, but still statistical work. And here, using the indices, we actually find a peak at the parallax. We filter them by age as well, using isochrones. And we conclude that we have 52 new variables in the region that are consistent with current members in terms of both their age and their distance, just not in proper motion, because that's the point. And in fact, we can see here, the proper motion is quite spread out. We can see that these little clumps right here are what were previously associated with the clusters. And then we have all these populations that are very, very, very dynamically different. And in fact, they go further out of the field, just that if I zoomed out too much, you couldn't even see, these look like little dots. But, very, very dynamic region. And we can also look at accretion with the photometry that we have. We can separate into accreting stars and weakly accreting stars that have H-alpha activity of different levels. And we can compare the populations that we find in those regions. And comparing them, we wanted to see how many are periodic in each one, right? Because generally, accretion has been associated with stochasticity. We find that 48% of the classical T-Tauri stars, so the stronger accretors that we find, are periodic, versus about 41% of the weak-line T-Tauri stars are periodic. These are, of course, subject to more contamination, but it's worth noting that weak-line T-Tauri stars are not more periodic than classical T-Tauri stars, which indicates that maybe accretion isn't the main driver of random stochastic variability, and there's more going on there. So again, this is a work in progress, and there's more to come in the next few years. Okay.
Okay, Trumpler 37. The better of the three clusters. So you want to agree, but he knows. So this is the Cepheus kind of constellation or association. So we get Trumpler 37 around this region. So this kind of border here is the field of view of North Face. So this is what the telescope is seeing. And we have the famous elephant trunk nebula here. Yeah, a bit of details about Trumpler 37. The distance, 925 parsecs away. It's 4 mega years. Speed of young stars. So that's kind of obvious, but yes. Okay, images. That's an image by Jose. Great image. A lot of details, a lot of cloud structure in there. So you can zoom in on the nebulae. We see quite a bit of detail, quite a bit of structure in there, a lot of embedded objects in there. So really potential sites for star formation. So, and this is an image by Vallejo. She was an Aurora student a few years ago, 2023. So what she did was look at IC 1396 H2 region. So that includes Trumpler 37. Should be this here. So like Ernesto already said, young clusters have a lot of substructure in them. So we still kind of see the same thing here. So these AVEF kind of, I use the name the substructure. So kind of shows that there's a lot going on in the. Yeah, let's go to the results. So we talked about light curves, talked about periodicity. So let's see where these kind of periodic objects are in the evolutionary track. So we have the main sequence would be here. So we have these. We can see that we are seeing sort of the main sequence, pre-main sequence kind of objects here. We see we have a lot of giant stars here, and our young stars are structured within the isochrones. So what's going on here is the increase in size and changes in color from blue to red would mean increase in the rotational periods. So that's a nice distribution we're seeing. We're also seeing that some of our giant stars are in sort of the process of jumping towards the giant branch. So they're still on the way there. So. Okay. That's as an example of an image by Rando, 2008. It has nothing to do with Trumpler 37. I just wanted to show you that there is presence of infrared access in most of our young stars. So you would see the spectral energy distribution. You would observe that kind of bump happening here. So usually a black body would kind of fall off here, a bit here. So you can see that bump there. That shows kind of infrared access. So which is linked to the presence of disks. So it's quite important. We can have a look at the YS. The YS that's on the y-axis and the 2 mass data. We get would find our objects on north face. We get the data from these two kind of catalogs, and what we see is there's a bit of separation, and we have the kind of the initial kind of group here, and we have this kind of group here. Yeah, there's a bit of a mess here with a lot of errors, but we're gonna ignore that for now. So what we are seeing is these kind of stars here in this sort of group here have a higher probability of having disks. So we see there's an excess in sort of YS and excess in 2 mass. So, and something similar to what Ernesto has already shown, we can look at the activity of our variable stars, more especially looking at sort of the accretion. So increase in sort of the accretion in sort of H alpha emission, and here's just changes in color, so reddening of our objects. So we have in pink here as a sample of objects that are known to be accretors from spectra. In yellow, we have potential young variable stars. And what we see here is these objects here are sort of the high H alpha emitters, so accreting objects. So we also see that we have potentially new accreting young stars, so here in the yellow. So we have potential new accretors there, which is exciting to see. We also yes. Okay. We also reached kind of the same result as Ernesto has already shown, that sort of most of our young accretors are periodic. So it brings in the question that is accretion sort of responsible for the stochasticity we are seeing in our variable objects, or is there something different at play? So that's kind of an interesting result, because previously we were saying the opposite thing. So yeah, we thought accretion was responsible for the chaos we were seeing, but we're seeing something entirely different. So, and we have this group of stars here. There's a lot going on here. We see some of these objects that are pink that are known to be accretors are sort of in the lower region of H alpha emission. So are they just low H alpha emitters? Might have to investigate that further. We see also that some of these stars here have disks. So it kind of shows signs that these kind of disks are evolving. So the inner regions are becoming more emptier. So the star doesn't pull a lot of materials, so lower H alpha emissions. And just a bit of extra information. The kind of giant stars we are seeing. So we are seeing some carbon stars, we are seeing long period variables. So they kind of occupy a more redder region here. So I haven't done much on this. I just wanted to put them there so that you know there's something there that exists. Anyway, like I said, if you're interested in giant stars and all that, you have a lot to work with. We can move a bit further and concentrate on our young stellar objects. So we can divide them into the ones which have disks and accretion, and those which do not have those. So essentially the classical T Tauri stars versus the weak line T Tauri stars. And what we are seeing here is sort of the weak line T Tauri stars are faster rotators compared to the sort of classical T Tauri star. So, and that's because of because of disk locking. So essentially classical T Tauri stars have the disks around them. So as there's that interaction between the star's magnetic field with the disk. So under certain conditions, you get that locking happening. So as the star is rotating, it has to pull the disk too. So you kind of get in that slow rotation than what's expected. So that's why we have the sort of weak line having that fast rotation compared to the classical T Tauri star. Yes. Oh yeah, and on something kind of different, we usually get supporting kind of observations as spectra. So we usually use the Osiris and the Hector shell to get spectra for this kind of variable objects. So I'm currently waiting on spectra from Osiris, so that's exciting. Maybe I'll have the data next month, hopefully. So yeah, and we would like to introduce this tool here called StarMelt by Campbell White. He's part of the North Face. So essentially, it's a Python package used to kind of analyze spectra of our objects. So we can get a lot of kind of information about this. It automatically detects kind of the different spectral lines. You can get the sort of the radial and angular velocities. You can even do the sort of the time analysis per line. So I personally haven't worked with this yet, so I'm really looking forward to it when I get the sort of spectra from Osiris. So another exciting thing. Yay. Yeah. So this is some of the results by Ruhi. She's on her final year PhD. So she's used StarMelt and she found some interesting results here. So she's looked at the sort of H alpha and the calcium lines, which are associated with the sort of the accretion processes. And she's also looked at the sulfur, which has more to do with sort of the outflows we are seeing from the stars. So you can do quite a bit of physics with this. Yeah.
So for the people that might be more interested, not in young stars, but in other objects, we showcase a few other things that North Face we've seen can do in the first year. And one of the first things we saw, which was quite surprising, was that in the deep catalog, we were actually picking up a lot of like late M-type brown dwarfs. And not only were we picking up, you can see they're you know, quite red, right? But not only are we picking up a good amount of known brown dwarfs, there's a lot of work to be done to pick up possibly new brown dwarfs and get their light curves. So again, this isn't a particularly beautiful light curve. However, it is the light curve of a brown dwarf. So if anyone is interested in doing time-resolved, you know, photometry of very low mass objects, there could be an opportunity here. At the same time, just it's a large field of view, and we have quite a few of them. So we actually do catch some transients. Here's a solar system transient object 324 Bamberga passing through the NGC 1333 field. I only put one image. You can see it over the various days going through the field, but here you can just see how it's not there. What? It's there. Okay. And we want to like kind of wrap things up a little bit by saying that we're currently in the process of studying a citizen science project to help classify light curves into the different object types, and it's you know, based on, it'll be called the Wilhelmina and Johanna School for Variable Stars. It's based on the story of Wilhelmina Fleming and Johanna Mackey, two young women from Dundee that emigrated to the United States to Harvard to work as cleaners. And while they were working there, they were scouted essentially by the person whose house they're working with, the lead of the astronomy department, and he put them to do work in astronomy. So you know, doing a lot of the calculations, which a lot of women used to do back then, and they classified, you know, hundreds and hundreds of objects, and essentially helped facilitate making stuff such as the HR diagram, right? So we're gonna be doing it in local areas mostly, but there'll be online tools. And one of the things that we also developed is an intuitive like Jupyter Notebook system. So people that don't know how to code, or maybe you're interested in learning but you know haven't been exposed to it yet, can look at all the different north phase objects and plot them and essentially look at how it works and essentially make phase folded diagrams and start classifying these objects. And that way, you know, we give back to the community by sharing the science that we do, and they give back to science and contribute to science by you know, supplying real important information that we need. Because again, very large fields and checking them by eye, it's a little bit hard. And so we'll leave you with our summary, which is just that time-resolved data can give information that you really can't get with anything else, especially when it comes to these young stars that are very, very active close to the stellar body. And that's why we have north phase. And we find a lot of the young variables are actually periodic, which is an interesting result. Because again of the aforementioned stochasticity thing, where you know young stars accrete, accretion stochastic, why they're periodic. And in IC 348 we find these objects that are associated with the cluster but don't share proper motions, which is a sign of processing of the cluster environment, which again deepens how complex the history of the region is. And again, accretion not necessarily fully stochastic from what we see. And public engagement. In the future, we've also been improving catalogs by characterizing. First, you characterize the variability, and then based on that, you can actually find an appropriate baseline of the star. For example, for dippers, right? You're gonna have a baseline, and then when something passes in front of the object, it dips down and it goes back to the baseline. But normally, if you just calculate the magnitude, if you catch it in a moment or average it out, it might be pulled down to a lower brightness. So we've actually had a bit of success, you know, recalculating some stellar parameters for instance, yeah, magnitudes of that. So that's in the future, but thank you for listening to our talk.
Okay, so thank you, Ernesto and Ferdinand. Do you have any questions?
I'm curious about the periodicities. Are you planning to derive p dots for those periods?
Sorry?
P dots, the variation of the period. Are you planning to derive those quantities?
Yes.
Yes,
that's not done yet.
Yeah, that will be interesting to evaluate the efficiency of magnetic braking in the systems.
Mm-hmm. Yeah.
Hi, thank you for your presentation. Sorry for my naive question, but what could explain that asymmetrical double peak of H alpha that you showed just a few slides ago?
Here. Oh. Next. Nice. Do you want to take it? Okay. Okay. I mean, again, we haven't worked too much with spectra, but based on what we know, it essentially means that there are different components. So if the asymmetric peak means that the wind is more prominent or the accretion onto the star is more prominent. And usually the wind will be the bluer side of things because it can be, it has that velocity towards maybe the line of sight versus the other H alpha maybe the other way because it has the inflowing from the accretion columns. Again, we'll have to, don't trust that answer 100%, but from what I understand, it separates the wind component from the accretion component.
Okay, thank you.
Hi, thank you for the presentation. It was great. And I have a question about membership because when we talk about clusters, I have that view of stars close to each other, not exactly at the same distance, but more or less similar movements. But you guys told us that it's not that simple. And I would like to know a bit more about your views about the movements, the dispersion and the distance factor, how far the stars can be from each other, and what can trigger the movements dispersion mainly, and to know a bit more about how you guys do the membership classification.
The membership classification, it's more based on the, like you said, the distance. So that's essentially parallax. You'd base it on the, I don't know if you do proper motion. Yeah.
Sorry. It's because I did, as part of my master's, I did some of this analysis for Perseus. And what we do is a clustering, essentially, of a maximum likelihood clustering of all the stars in the region. So we start with a sample that's already in the region, and based on that we do further clustering and find differences, like more fine differences between the proper motions and the parallaxes. Proper motions, parallaxes, and it's with Gaia data, so we also use their correlations. And based on that, we can then characterize different subgroups and then find new members consistent with those subgroups. So the memberships that I showed are all in the optical, because we're looking at the optical, but they're also they're also added with members that we found in our analysis. What's the second part of your question? I forgot.
I asked you about the movement dispersion because
Yes.
you showed a graph with some members moving very differently from the major dispersion. Then I would like to know more about what could be happening there.
Yes, this one. Go to the one with the two. Next, yeah. Okay, this one. Okay, so we're not 100% sure. That's why what we're doing is we're studying the properties of these stars and seeing how they differ from the properties of the stars that are consistent in proper motion. What we do see from some of the literature is in, for example, the cluster simulations by Matthew Bate. You do see that these clusters, as they start forming, they contract onto the filaments, and then some of these objects that were forming in the early periods get ejected because of dynamical interactions, and then you get further star formation after these ejections happen. So a hint would be to the older populations that formed at the beginning of the star forming episode in the molecular cloud. Yeah, so that's what we think. We're still looking at it. We're trying to look at differences in spectral types, And yeah, that's why we get spectroscopic follow-ups, especially for members that are quite interesting, right? So these variables that are behaving in a strange way. But in general, we think it's because of pre-processing of the group, and then you get further star formation. Which is, in fact, this is the IC348 members. This is IC348, right? So that's the NGC proper motion, but these members are associated with in the IC348 field. And that one has a very large age range. So the members that we find associated to it in proper motion are from 2 to 6 million years. So that indicates that, you know, there's been pre-processing, which normally, based on the simulations, a lot of this pre-processing can start happening at like 3-4 million years. So yeah, we're expecting that. We don't know, but we'll keep you posted. Yeah.
Any other questions?
So thank you for the talk. So yeah, in this image, it's perfect there because I wanted to ask about that too. Because for us, it's like when we're trying to characterize a cluster, like a star cluster, a young cluster, we try to like, are these all Gaia data, the proper motion and the parallax? It's all Gaia.
Yep.
Okay. So yeah, we try to like do cuts in the parallax in the proper motion to try to like figure out what belongs to a cluster or not. So for me, it's kind of surprising to see like things that do not fall exactly like very close in the proper motion be characterized as part of the cluster. So like those blue dots, they in the parallax, they were kind of like similar to the.
Yes.
Okay.
Yes.
So one of my questions is, do you guys also have some kind of like a quality cut in the like a signal to noise ratio in the parallax of Gaia or something like that?
Yeah.
Did you apply this?
We do. The general quality cut, it's not super restrictive. It's 0.2. Like if the error is over 0.2, the parallax, we get rid of it.
Okay.
You know, the ratio, yeah. The error to parallax ratio has to be below
like
0.2.
The signals are okay.
Yeah.
Okay.
That's it's not like super restrictive, but it seems to maybe be okay. But these objects aren't on the upper end of that. They're, you know, they have decent parallax estimates.
Okay, yeah, that was one of my questions because I also had to apply that. And just one more question. Just I don't think you have to go all the way back, but like when you were talking about like the photometry calibration and you show like this linear relation, there was like one very much like outlier in the first. I just like to know. Do you guys know what happened to that? It's like in the, you know, the calibration with the photometry, there was like 1 point all the way up.
Well, we've done some experimentation with that. We can go back while I go. But
That's not very good.
we've done some experimentation with that, and we see that the synthetic photometry essentially that is generated by Gaia XPy, it proves very good generally. No, after.
Before, yeah.
There, yeah. So it proves very good generally, but there are certain situations if the object has a very strangely behaved spectra, that it can, you know, if it has big absorption lines in a certain spot, that it can fail. It's just that on a statistical level, to generate the calibration, it works well. In fact, we were at the S+ meeting in Rio, and they were talking about 0-point maps for these fields, but for the S+. And so we were like, okay, well, we haven't like looked too much into the difference between the synthetic and the measured for ours, so like in terms of distribution. We find that in the 0-point maps, there is a bias to like essentially the calibration. It gets worse as you go to the edge of the field, which isn't like a crazy result, but yeah. And so this object, it has a Gaia non-variable counterpart. It has a spectra, but it could just be that it's at the edge of the field, and so the north phase measurement is a bit more off.
And do you kind of like, do you create like a flag for that? Because like
yes, we create flags for loads of things. That's part of the calibration process. We have flags for objects that are right on the edge of the field, because those, especially with variability, sometimes they're slightly in, sometimes they're slightly out, because the telescope positioning changes very slightly from image to image. We also create flags for objects that have a lot of cloud behind them, because those can be very messy as well. So yeah, you just need to be a bit careful with those. And we create objects, like flags for objects that are very close to other objects. Our way around that is in the second year of data, which isn't complete yet, we have different sized apertures. So we do the photometry with different sized apertures and with PSF as well. So we have 2, 3, and 5 pixel apertures. And depending on the objects, so depending on the flag, we'll have to use one or the other. So again, the ones on the edge of the field and the ones near other companions, most likely going to use a smaller aperture, which isn't as amazing, but if there's other stuff around it, you know, there's issues. Or with the brown dwarfs, they're usually quite small, 2 pixel apertures. So yeah, we're creating these ways of you know, getting around these problems that present themselves. Yeah,
Thank you.
of course.
Any more questions? Questions online? No? Okay, so let's thank our speakers again. Se alguém esqueceu de assinar a lista, tá aqui, tá?